Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry paper 4. This is lecture 4 of module 2. We are discussing the aspects of electrochemistry. Now friends, till our previous lectures, what we have we have seen the cell representation, we have seen EMF of the cell, we have seen the numericals based on calculation of EMF of cell. Now we need to see what are the relations between thermodynamic quantities and the cell EMF so that it can be applied, the gained knowledge can be applied to the calculation of thermodynamic quantities. So what are the thermodynamic quantities which we can find out? Say free energy, enthalpy, entropy, and so on. So once I get the knowledge of these quantities, I can relate the application of the calculation or measurement of EMF to the various processes. Okay, so to start with, let us say first we will try to find out the relation between free energy and the EMF of the cell. So what is basically free energy? We have all seen the definitions of free energy from our early school days. So Gibbs free energy, what it is actually? So Gibbs free energy basically could be determined as the thermodynamic potential, which can signify the reversible or maximum amount of work that can be performed by a thermodynamic system, and that thermodynamic system should be under constant pressure and temperature. So we can find out in this way the Gibbs free energy. Now the work done by electrical power within 1 second is actually prescribed by the product of total charge passed through the solution and the EMF of the cell. Okay, so if I have n number of electrons and if I have passed the electricity of say 1 Faraday, so I can calculate that how much is the total charge which I have passed through the solution. Now we know that any reaction or the process will be called as spontaneous if the free energy is negative. If delta G is negative, my process is spontaneous. If delta G is positive, I call that process as non-spontaneous reaction. And when delta G is 0, we call that process as in equilibrium. Okay, this is the standard convention. Now, in an electrochemical cell, when the charge is reversibly passed through the galvanic cell, it can be noted that the maximum amount of work which is completed by the galvanic cell uh, is actually given, it should be given by, or it should be related to the EMF of the cell. So therefore the amount of the reversible work done by the galvanic cell results, or basically I would say it is responsible for the decrease in Gibbs free energy within the reaction, and therefore as a result of spontaneous redox reaction the free energy of the system will decrease, and therefore this negative sign comes over here. So my free energy change is proportional to EMF of cell. That way it is correct. But then when the work has been done, there is a decrease in free energy, and therefore this negative sign comes over here, and therefore delta G is equal to minus NFE. This decrease in free energy is responsible for the generation of EMF basically. Okay, so we can see over here this decrease in free energy, it is proportional to EMF of the cell, and this decrease in free energy is responsible for the generation of EMF. Now suppose N is the number of electrons involved in the cell reaction, and F is the Faraday constant, and E is the cell EMF, then the amount of electricity generated is equal to actually NFE basically, isn't it? And it should account for the decrease in free energy, and therefore delta G is equal to minus NFE. So this is generated at the cost of free energy change delta G. As we know that the Gibbs energy of a reaction is known to be an extensive thermodynamic property. What does it indicate? It indicates that its value depends on N. So therefore, when a two cell reaction involves varying values of N, it can be observed that the values of Gibbs free energy also vary, and therefore it can be related in this pattern that delta G is equal to minus NFE. if I follow, or if I keep the standard conditions while carrying out this operation, so under standard condition I can relate the same expression of equation 32 as delta G standard is equal to minus NFE standard. So this will be standard EMF of cell. Okay. Similarly, I can find out the relation between enthalpy change and the EMF according to Gibbs-Helmholtz equation. Now, what is my Gibbs-Helmholtz equation? My Gibbs-Helmholtz equation is delta G is equal to delta H minus T delta S. Now, that delta S can be represented as minus ddt of delta G, and therefore I can write down delta G is equal to delta H plus T into ddt of delta G. Now I can substitute this value of delta G from this equation 32 or 33. So if I substitute the value of delta G, so delta G is equal to minus NFE. Therefore, minus this equation 34 would take the shape of minus NFE is equal to delta H plus T into ddt of minus NFE. If I substitute this value, I get this expression of equation number 35 as E is equal to minus delta H upon NF plus T into dE by dt or ddt of the cell EMF. Okay. Now this in this particular equation of 35, this particular equation, the left hand side is the electrical energy, while the right hand side is the thermal energy. So the factor dE by dt, this dE by dt is called as the temperature coefficient of the EMF, and it is defined as the change in EMF per degree change in temperature. You can see over here, change in EMF per degree change in temperature. Okay, so if you look at this particular equation, this 35, so if the temperature coefficient is 0, then cell EMF becomes independent of temperature, isn't it? Cell EMF becomes independent of temperature, and hence electrical energy supplied by the cell is equal to enthalpy change in the reaction. So electrical energy will be the enthalpy change. Whereas if the temperature coefficient is positive, then the electrical energy supplied is greater than the enthalpy change of the reaction, and this additional energy is absorbed from the surrounding. And similarly, if this coefficient is negative, then the electrical energy supplied is less than the enthalpy of reaction. In such case, the additional energy is given to the surrounding. This is how we can relate the outcome of this relation of thermodynamic quantities with the cell EMF. Similarly, we can find out the entropy change that has to be related with the EMF. Now, in case of this, in order to find out the relation between entropy change and cell EMF, we again will start with Gibbs-Helmholtz equation, that is delta G is equal to delta H minus T delta S. So I will substitute the value of this delta S, that is minus of ddt of delta G, and therefore delta G is equal to delta H plus T into ddt of delta G. You can find out this expression using Maxwell's relation. If you know the Maxwell's relation, you can very easily relate with this, that how this delta S can be related to the free energy. Okay. So this comes out to be ddt of delta minus of ddt of delta G in case of delta S. So this minus minus will become plus. Therefore, delta G is equal to delta H minus, if I substitute delta G is equal to minus NFE, so I can write down this expression again as delta G is equal to delta H minus NFT into dE by dt. Okay, this is temperature coefficient. Now this delta G, since delta G is equal to minus NFE that we have substituted over here, these two equations on substituting, I can calculate from this particular part delta S. So directly from if I substitute, instead of delta S is equal to minus ddt of delta G, I can, if I substitute this value over here, so delta S is equal to NF into dE by dt, I can directly substitute, and that way I can obtain the expression for change in entropy, and this can be related with the EMF of the cell. Okay. Similarly, I can find out the relation between equilibrium constant and cell EMF. Okay, so for this, let us consider a cell reaction in thermodynamic equilibrium. There are innumerable number of applications of these thermodynamic relations. We will see one full dedicated lecture on this particular part. So let us consider for time being a general equation wherein some kind of chemical thermodynamic equilibrium is like this, represented by equation 39, that A into A plus B into B is in equilibrium with C into C plus D into D. So this is reactant side and this is product side, say for example. Now according to Van 't Hoff reaction isotherm, what I can write down? I can write down that delta G is equal to delta standard plus RT ln of this activity of product upon activity of reactant. Okay. So I know that delta G is equal to minus NFE and delta G standard is equal to minus NFE standard. So if I substitute over here, I get this particular expression taking the shape of this. E is equal to E standard minus RT upon NF, ln of product of activities of reactant side upon product of activities of product of activities of product side upon product of activities of reactant sides over here. Now we also know that the standard free energy change delta G is related to equilibrium constant, that is cell constant, in this fashion, that is delta G standard is equal to minus 2.303 RT log of K. Okay, so or minus RT ln K also we can write down. So we have converted into natural log into this log to the base 10. Now if I substitute the value of delta G standard over here, so it will be minus NFE standard is equal to minus 2.303 RT log K, and therefore I can find out standard EMF expression as 2.303 RT upon NF log K, and therefore log K can be found out as NFE standard upon 2.303 into RT. So I can find out this way the relation between logarithm equilibrium constant K with the EMF of the cell. There is very important relation. It is known as Nernst equation. Now this Nernst equation is actually the application of this cell EMF, and if we can find out the thermodynamic relation between quantities, we get the output as Nernst equation. Okay, so in this particular case, if you see the relation between concentration and cell EMF, uh, if uh, if I could arrange, so this equation leads to the Nernst equation. Now let us again consider a cell reaction in thermodynamic equilibrium. What it is, it gives me the general chemical reaction. If I consider, there are innumerable number of applications of this Nernst equation in a particular potentiometric applications. If you consider this general chemical equilibrium reaction, so free energy change in the reaction is given by Van't Hoff reaction, and this is given by delta G is equal to delta G standard plus RTLN product upon reactants. Okay, but this delta G is equal to minus NFE and delta G standard is equal to minus NFE standard, and therefore minus NFE is equal to minus NFE standard plus RT ln of products upon reactant. So I can rearrange it as E is equal to E standard plus RT upon NF ln of products upon reactant. So further I can rearrange this natural logarithm into this log. So E is equal to E standard minus 2.303 RT upon NF log of products upon reactant. This particular equation 42 is known as Nernst equation. Okay, there are n number of application of this Nernst equation, and we will see while looking for the application of the electrochemical or the knowledge which we have gained in this particular lecture series. At 25 degrees of centigrade, this 2.303 RT upon F, this factor comes out to be 0.0591. This we know very well, and therefore my expression 42 converts into form, or it takes in the form of E is equal to E standard minus 0.0591 upon N log of products upon reactant. Now this value of E and E standard are the oxidation potential and standard oxidation potential of the cell respectively. So oxidation potential and standard oxidation potential. Now if I use the reduction potential as the IUPAC standards are there, we have to use the reduction potential. This minus sign converts into plus sign, and therefore this equation 43 reduces its form or converts its form to this form, that is E is equal to E standard plus 2.303 RT upon NF log of product upon reactant. So this is basically, there is a very basic difference that whenever we use oxidation potentials, this form is applicable of Nernst equation, and whenever we use the reduction potential, this form is particularly applicable of Nernst equation. Okay, let us see its application. Let us say that I have to calculate the free energy change of the cell. We will see how this relation can be applied. So very simple example, the EMF of the cell. If this is a cell wherein cadmium electrode in contact with the cadmium ion solution, and silver electrode in contact with the silver ion solution, and both of them, they are in contact with each other through a salt bridge. So this cell is there, and whose EMF is given as 0.673 volts at 25 degrees centigrade. Now we need to calculate the free energy change of the cell. So we can write down the cell reaction. This cadmium is going out cadmium from cadmium electrode, that is at anode. The cadmium ions are going to solution. Two electrons are generated. These two electrons are consumed by the silver ions from the other cell, and the silver is precipitated at the cathode. So overall reaction is this. Now therefore the number of electrons involved in this particular reactions are 2, and therefore delta G is equal to minus NFE. So N is 2. Okay, so if I substitute all the values, delta G is equal to minus 2 into F is, that is Faraday's constant, is 96,500 into what is the EMF of cell? It is 0.6753. So if I substitute over here, I can find out delta G is equal to minus 130332 joules per mole, or 130.332 kilojoules per mole is the free energy change. Similarly, I can go for many other applications, or many other numericals, but as a matter of fact, I need to look for several numericals because they are important from the point of view of understanding the concept, and therefore we will see several numericals based on this concept. For example, look at this example 7. Now in this example, what we have considered, calculate the standard EMF of cell. Now EMF has to be calculated. What is the cell? This is just like a Daniel cell. Now zinc in contact with the zinc ion of 1 molar, that therefore standard EMF is given, and copper is in copper ion copper electrode is in contact with the copper ion, and which is also 1 molar, and therefore standard EMF, standard conditions are maintained. And both of these electrolyte solutions and their electrodes, they are in contact with each other internally by salt bridge. Now given that the free energy of formation of zinc 2 plus and copper 2 plus ions are minus 147.03 and 65.52 kilojoules per mole respectively. In case of zinc, it is minus 147.03 kilojoules per mole, and in case of copper, it is 65.52 kilojoules per mole. It is given. Now what we need to calculate? We need to calculate the EMF. So again, we have a formula. What is a cell? That is, the cell representation is like this. So cell reaction is like this, because we know now in this case how many number of electrons are involved, that can be calculated. So there are two numbers of electrons are involved, at anode, at cathode. Both the reactions are going on. So delta G standard is equal to this. Why it is standard? Because 1 molar solutions are used, and therefore delta G standard is equal to, for zinc it is minus 147.03 kilojoule per mole, and for copper it is 65.52 kilojoule per mole. Now I can actually substitute it over here. So delta G of this overall cell can be calculated as this much joules. Okay, so delta G standard is equal to minus NFE. So I will substitute all these values over here, and I can calculate the standard EMF. So it comes out to be 1.10 volt. This value, if you remember in our previous lecture, in lecture 2, I guess, we have calculated the EMF of this cell, of such Daniel cell which are connected with each other, and it comes out to be the same. So again, look at this place, that this standard EMF of the cell, such cell, is 1.10 volt. It again repeats over here. So it is a verification point as well. Similarly, you can see another example wherein we have been given with what we need to calculate free energy change for cell. So what is the cell? It is given zinc in contact with the zinc ions. Activity is 1. That means again a standard condition. And silver electrode in contact with the silver ion, and activity is 1, again a standard condition. Both of these electrodes are in contact with each other through a salt bridge. So my standard electrode potential for zinc is minus 0.76 volt, and standard electrode potential of silver is 0.80 volt. And therefore if I go for the looking at the overall reaction at anode, this is happening. I mean, this zinc is leaving zinc ions into solution, and 2 electrons are released. At cathode, these 2 electrons are absorbed by the silver ions, and silver metal is deposited at the silver electrode. So overall reaction is this. So number of electrons involved in this process are 2, and therefore I need to calculate the standard EMF of the cell. So standard EMF of the cell is equal to standard EMF of cathode minus standard EMF of anode, isn't it? So, or I can write down that standard EMF of right hand cell minus standard EMF of left hand cell. So I can substitute these values. So standard EMF of cell is equal to this, at cathode I have silver, so it is 0.80 volt, minus what is at anode, that is for zinc it is minus 0.76. So 0.80 minus plus 0.76, it gives me 1.56 volts, isn't it? So once I get the standard EMF of the cell, I can substitute this EMF into this formula. So delta G is equal to minus NFE standard. So delta G standard is equal to minus NFE standard. Therefore, N is equal to 2. I will substitute. So minus 2 into Faraday's constant is 96,500 into 1.56 is the standard EMF of the cell. And therefore, I get this result of minus 301.080 kilojoules is uh, the amount of free energy which is generated or which is spent for this particular cell reaction. Similarly, I can go for other numerical, that the EMF of cell is given as 0.536 volt at 298 K. Now, if I need to calculate delta G, delta S and delta H, if the temperature coefficient is 0.145 millivolt per Kelvin and N is equal to 2. So everything is given. We have seen all of these formulas, and therefore if I would like to substitute these values in the formula, I get very easily the values I can get very easily these values. Let us see how. Now what is given? We have been given with the EMF of cell, that is 0.536. We have been given with N is equal to 2, number of electrons involved. We have been given with temperature. Temperature is involved, that is at 25 degrees centigrade at 298 K. The temperature is maintained, and therefore, and also the temperature coefficient dE by dt is given as 0.145 millivolt per Kelvin. So I can convert it into volts. So it is 0.145 into 10 to the power minus 3 volts per Kelvin. So if I substitute the values of EMF in delta G is equal to minus NFE, so I get delta G, that is minus 2 into 96,500 into 0.536. So I get minus 103,448 joules is the value for free energy. Okay, now once I get free energy, I can actually calculate the delta H. Let us calculate delta H, because for this we do not need delta G. Delta S is equal to NF into dE by dt. This we have seen by formula. So I have all the values. So if I substitute, N is equal to 2, F is equal to 96,500, and dE by dt is equal to 0.145 into 10 to the power minus 3. The value comes out to be 27.985 joules per Kelvin. That is delta S. Now I know the Gibbs Moles equation, that is delta G is equal to delta H minus T delta S. Okay, so delta, if I substitute all the values over here, delta G, if I rearrange this, delta H is equal to delta G plus T delta S. So I will substitute the value of delta G, I will substitute the value of delta S, I know T. If I substitute all the values, I get delta H is equal to minus 95,108 joules. So this way I can calculate all the thermodynamic parameters based on the value. If I know the EMF and if I know the temperature coefficient, I can calculate all the three values that way. Okay, or if I know the several values of EMF at varying temperatures, so I can very easily calculate temperature coefficient by plotting, by taking slope of dE by dt, EMF versus temperature, and therefore I can very easily calculate dE by dt even in several cases. So that also can be done. So just for the sake of simplicity, the simple value of dE by dt is provided over here, and therefore we could very easily calculate. Otherwise, in some numerical, the temperature dependent values of EMF also is given, and then it is an indirect indication that you need to calculate the temperature coefficient dE by dt, and by calculating the dE by dt, then you can calculate the delta S. Okay, so this way also one can go for this numerical. So similarly, let us have a look at one type of numerical which can be appeared. So in this numerical, what is given? The standard hydrogen electrode is connected with the Kelvin electrode, and the EMF of the cell is given as 0.2676 volt at 298 K. This is a cell reaction particularly involved, and its temperature coefficient is also given, that is minus 0.000319 volts per Kelvin. Okay, so it is given in volt per Kelvin. Now what we need to write down? We need to write down the cell reaction and calculate delta G and delta H of this reaction. Okay. So for this, what is being given? It is given that E is equal to 0.2676 volt at T is equal to 298 K. Also, this temperature coefficient is also given. That dE by dt is equal to minus 0.000319 volts per K. So the cell reaction can be written down that at anode, this particular reaction is taking place. This is half cell of anode, and this is half cell reaction of cathode. So two electrons are released at anode, and electrons are absorbed at cathode, and therefore the overall net reaction is this. Okay. So number of electrons involved is 2, and therefore delta G is equal to minus NFE. Therefore minus 2 into 96,500 into 0.2676, that is 51.646 kilojoule per mole. Now we have also derived the relations of direct relation of EMF in this form as well. So EMF E is equal to minus delta H upon NF plus T into dE by dt. This we have already derived by keeping the value of delta G is equal to NFE into the expression, that is gives a Morse equation. So this can be directly obtained, and therefore if I convert this expression in terms of delta H, so I get this expression of the form delta H is equal to NF into T into temperature coefficient minus E. Okay, so now what I have all these values. I have N, F, T, this temperature coefficient, and E. So I will substitute all these values, that is 2 into 96,500. T is 298, temperature coefficient is minus 0.000319 minus 0.2676, which is equal to 69,994 joules, and therefore my delta H is equal to 69.994 kilojoule per mole. Okay. Similarly, I can utilize other type of this expression for other type of cells as well. Let us take this example. In this cell, this cadmium is in contact with cadmium chloride, and silver is in contact with the silver chloride, and both of the half cells are connected by a salt bridge, and the EMF is given as 0.6753 volts at 25 degrees centigrade and 0.6915 volt at 0 degrees centigrade. At two different temperatures it is given. Now calculate free energy change and enthalpy change of the cell reaction at 25 degrees centigrade, which is given. So we have been provided with the two EMFs at different temperatures. So EMF E1 is equal to 0.6753 at one temperature, that is at 25 degrees centigrade, that is at 298 K, and the other EMF is at 0.6915 at other temperature of 0 degrees centigrade, that is at 273 K. So the cell reactions can be obtained as at anode cadmium is giving to cadmium ions and releasing two electrons. These two electrons are absorbed at cathode by silver ions, and silver is liberated at cathode. So the overall reaction is this: cadmium plus twice silver ions plus cadmium ions, which will give you cadmium ions plus two silver atoms. In the overall reaction, there are two number of electrons involved, and therefore N is equal to 2, and therefore delta G is equal to minus NFE, which is equal to minus 2 into 96,500 into 0.6753. So it comes out to be minus 130333 joules per mole, 1,30,333 joules per mole. That is nothing but minus 130.333 kilojoules per mole. Okay. Now I can find out dE by dt, that is temperature coefficient for this particular two EMFs, and at two temperatures it is given, and therefore dE by dt can be written as E2 minus E1 upon T2 minus T1 very easily. So if I substitute over here, it is 0.6915 minus 0.6153 upon 273 minus 298. So it gives me minus 6.48 into 10 to the power minus 4 volts per Kelvin. So I can get this temperature coefficient in this fashion. We have just now discussed this part in two numericals back, and this is what I wanted to convey, that dE by dt can be calculated using such kind of data as well. Okay, now this EMF is related by the expression this, which we have seen just now. E is equal to minus delta H upon NF plus T into temperature coefficient. So I need to find out delta H. So in terms of delta H, this expression can be rearranged as delta H is equal to NF into T into dE by dt minus E. So if I substitute all the values over here, so N is 2, F is 96,500, T is 298, because we have to calculate the enthalpy change at 25 degrees centigrade, and therefore we have substituted 298 over here. dE by dt is minus 6.48 into 10 to the power minus 4 volt per Kelvin, minus 0.6753 is EMF at 25 degrees centigrade. Okay, and therefore it comes out to be around minus 167.602 kilojoules per mole. So free enthalpy change for this particular cell is minus 167.602 kilojoules per mole. Similarly, I can calculate the equilibrium constant for the following reaction. If this is the reaction, if I substitute this value, I mean what is given, we have been given with R value, Faraday constant, and EMF is given, that is for zinc and for copper. The EMF values are given. Now we know that this E cell is equal to E right minus E left, or EMF of cathode minus EMF of anode, and therefore if I substitute this value, I get the standard EMF of cell as 1.102 volts, and therefore I can calculate the EMF, or I can calculate the equilibrium constant, which is related to the standard EMF of cell as log K is equal to NFE standard upon 2.303 RT. If I substitute all the values, I get log K is equal to this, and therefore K is equal to anti-log of this, which comes out to be 1.88 into 10 to the power minus 30, 1.88 into 10 to the power 37. So this is how we can calculate the K. This type of numericals can also apply, or it can be appeared. Say what is given, we need to calculate the EMF of Daniell cell at 25 degrees centigrade. If zinc sulfate and copper sulfate solutions are 1 molar and 0.1 molar respectively. So zinc sulfate is 1 molar and copper sulfate is 0.1 molar. Two different concentrations are given, and E standard for the cell is 1.1 volt for this Daniell cell. So if it is given, what can be done? Daniell cell is represented like this. Concentration C, zinc cell is 1 molar and copper cell is 0.1 molar. Now the cell reaction is this, and therefore N is equal to 2. So I can substitute this value in the Nernst equation. I have Nernst equation, that is E is equal to E standard minus 0.0591 upon N into log of the product side, concentration of product side upon concentration of reactant side. So if I substitute all the values, E standard is given as 1.1 minus 0.0591 upon N log of 1 cross 1 into 1 upon 0.1 into 1. All the values are with us, and therefore if I solve this, I get the value as 1.07 volt, because I know that there are number of electrons involved are 2. So if I substitute this value as 2, I get the final expression, final value of EMF is equivalent to 1.07 volt. I can calculate this way for n number of numerical or examples. I can calculate the EMF of the cell by putting the values of their concentration in the Nernst equation. And this for solid copper and zinc, the activities, since we take unity, and therefore we have taken 1 over here, that one has to keep in mind. Okay, so for copper and for solid copper and solid zinc, copper electrode and zinc electrode, their activities is considered as 1, and therefore the values have been taken as 1 and 1 over here, whereas these two represent their concentration. So zinc concentration and copper concentration is given as 1 and 0.1 respectively. Similarly, if you consider the this example herein, calculate the EMF of zinc silver cell at 25 degrees centigrade when zinc ion solution is given as 0.1 molar and silver ion solution is 10 molar. So standard EMF of the cell is 1.56 volt, it is given. Similarly, I can calculate here that the cell reaction is this, and therefore N is equal to 2. So Nernst equation, if I apply, I get this formula, E is equal to E standard minus 0.0591 upon 2 log of this product side upon reactant side. So if I substitute all the values over here, so I get 1.56 into 1.56 minus 0.591 upon 2 into log of 0.1 into 1 upon 1 to 10 to the power 2. So it gives me 1.65 volts, isn't it? Now once again I can take like the for solid electrodes, the their activities, they are taken as unity, and therefore 1 and 1 values are taken over here. Okay, so friends, we will stop here in this lecture 4, and from our next lecture we will see the different types of electrodes. Thank you.